In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller...
All right, hello and welcome everyone to Celestial Theodolite update number 30. Last week we were discussing the central angle traversed and the half gamma of that central angle, which is just the central angle divided by 2. But before we get into that, we'll do a quick recap for what the Celestial Theodolite process is, what we're doing here, because there are some new listeners. So, the Celestial Theodolite is based on the null hypothesis. The Earth is flat, and the hypothesis being the Earth is a globe. So we have two mutually exclusive opposites here. And through this process of using star occlusions, we can make determinations about mutually exclusive angles over distance regarding mountain peaks. Now on a globe, there's going to be a drop over distance, which can be represented in this diagram. It looks a little cluttered, but I'll kind of break it down for you guys. So the globe is offset by curvature. The tangent to the horizon on a sphere is offset by whatever the drop over distance is of that horizon. So in the case of Pikes Peak, for example, the globe is offset by 13 arc minutes. That's the half central angle of the arc length there. The arc length being 27 arc minutes. They relate distance and angle through central angle theorem. So all of this just also applies to sky geometry, but regarding the elevations of mountain peaks, the globe predicts that this elevation will be whatever the flat Earth predicts minus the drop over distance here. So you could take the flat Earth prediction for rise over run to the peak of where the star would be geometrically aligned versus what the globe would predict, which is minus this 13 arc minutes here, which is the half of the central angle. Now you can also derive it through spherical trig and a bunch of other different approximations and whatnot, which are noted over here. But the easiest way to conceptualize this in terms of central angle theorem is that flat Earth is rise over run, globe Earth is rise over run minus globe drop, or it would be, rise minus globe drop over run. Sorry. Anyway, to be precise or whatever. But anyway, when an occlusion occurs, we're recording the time, so we know when the star was occluded, and using that we can reference angles. We can use the almanac or our favorite astronomy tool like Stellarium, etc., and enter the time at the observer location, see where the star's true position was, and we could also add the arc length back to the star's true position, and that will move it up to see what the geometric alignment would be over that peak, and if it's closer for the occlusion. So what happens is, what you can do is you could reference observer location, you can reference the peak, and by referencing where the star's true position is, which is the geometric alignment of what would be considered the light source, not the position of the star that you see, but the actual light source that's moving at 15 degrees per hour, 60 nautical miles per degree, plus or minus latitude variation. So in these comparisons here, if the Earth is a globe, then they predict that the star would be more aligned when it's at the angle 217 degrees. And for the observer, the globe being based on observer centric and then reduced, doing a slight reduction on the refraction to get the geocentric angle, all based on this single observer, observer centric view for where the star should be with respect to that peak. So considering their drop over distance and how that relates to the sky, the globe essentially predicts that 217 angle. Now, um, when you add the arc length back, and if it makes a congruent triangle with what flat Earth would predict, then that means that the star's geometric alignment, that the cause of the occlusion was because the star wasn't following the 60, 60 nautical mile per degree deviation at the horizon. Its true position was actually lingering. And we've plotted out what that lingering looks like here. 1 second, I'll pull up the diagram. But 1 second. Copy link. All right, so the celestial sphere here, this is like the stars following the ideal 60 nautical mile per degree as asserted, irrespective of the refracted position. This is just what the apparent would be. So the occlusions should line up with these, with this blue line here. But what ends up happening is they're always not where they should be. They're always off. And the reason for that, we're asserting is that the stars are not truly following what the globe says they are, and how they would have to be beneath your feet, following that 60 nautical mile per degree relationship to make that all work. They would have to be following that. But none of the occlusions correspond to what the globe predicts. The error is always the opposite. So to kind of get to what we were talking about last week with the occlusions, in every measurement, the comparison is done through the geometric position of the star with respect to the peak for flat Earth and with respect to the observer for the globe, and whichever one is closer to their geometric prediction, that would be the one who is more likely to be the cause of the occlusion, because that's how the geometry is going to work out. But in every case, we see that the flat Earth is off a little bit, and globe Earth is off by always a significantly more amount. But the more important part is that when we take these errors together, this 11 and this 2, and add them together, we get 13 arc minutes. So over the arc length, over the distance between the observer and the mountain peak, we have this relationship in time and angle. Now, the star, relative to the observer, has already traversed that arc length, because that's when the occlusion occurred. So we can't um, we can't get like a different number out of that, right? Like, because all we're doing, like when we move to the peak in stellarium, all we're doing is adding that arc length back for the comparison. So that's always going to be, so the gamma, and which is the central angle, that 27 arc minutes that defines that distance here, is always going to be there's always going to be a half gamma associated with that, which is half of whatever the central angle is. So half of the 27 comes out to be 13. So there's always going to be an elevation offset of whatever gamma is between globe Earth and flat Earth. And that's what's noted in this diagram here. So we have, to start us off, we have observer true angle equals theta, or is theta equals beta minus 90. And beta is whatever the star's true position is plus 90 degrees minus 90 degrees. So it just comes out to be 206 in the case of Pikes Peak. Seems like a roundabout way to do that, but it's the way you have to do it to solve for the triangle. So the 2 arc minutes and 6 seconds over here for the observer position that the globe predicts for the observer. They say that the star would be right here, and that's represented by this. So over the arc length here, we have this proportional ratio of half gamma. So half gamma has offset this mountain peak by 13 arc minutes. So the difference between flat Earth prediction and globe Earth prediction is this half gamma amount. So you see here, like the offset for that angle, that's what creates that, the mountain being tilted away because the globe geometry. So at the end of this arc length, there's 200 meters of drop or 13 arc minutes of drop. You can convert the arc minutes into meters using tangent or a Sagitta approximation. But anyway, in any case, that is the proportional ratio to these. So however much the globe is off on this at the end of this arc length, the remainder offset automatically goes to flat Earth because it's the same arc length, so there has to be a proportional offset to it. So when we talk about the air in the celestial theodolite, or why is this peak not lined up, blah 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 kind of thing. Well, the fact of the matter is, at the end of this arc length here, there's either a mountain peak that's rise minus globe drop over run, or there's just a rise over run peak. So the half gamma air is like a kind of like a math artifact that comes out of the asserted geometry that's supposed to be associated with it. So let me show you a quick example of this. So on Pike's Peak, where when you add the arc length back, we're off by 2 arc minutes, and keep in mind the occlusion occurred like in reality, like irrespective of where the perfect geometric alignments would be. And this is what it came out to be. We ended up being 2 arc minutes off. Globe ended up being 11 and a half arc minutes off. Now, if the Earth were a globe and they got their geometric alignment, it wouldn't be the central angle that would be a different amount like I had previously thought. It would be strictly that air in the half gamma, because the full central angle has already been traversed. So there's no more like the star can't go any further, it can't get any lower. It's already done that amount relative to the observer. So if you so anyway, what I was trying to do, I made a mistake in looking at the half gamma, and then I would like try to recover the full gamma amount from that, but that's not a it's not how that works. It just becomes circular at that point. So anyway, if you look here, if the globe gets their occlusion at 217, when we add that arc length back, we're off by 13 arc minutes. We're off by the half gamma. The star got occluded earlier than what we predict because it didn't have time to get lower relative to the peak. It didn't have to. It was already geometrically aligned based on the geometry of the ground and the sky in conjunction together. The only way that you would get an air offset where these are reversed is if the curve was only in the sky and didn't exist on the ground. So, so let's see here. Back to this right here earlier, like I was saying, adding the central angle back to the to the star to get what the flat Earth would predict. This psi here is equal to the arc length plus the original starting angle. So if you add 23 arc minutes to this, or I'm sorry, if you add 27 arc minutes to the observer true position, you get 233. So in short, I was wrong about how I was articulating the central angle change relationship. The error would strictly be in the gamma difference, because that's the actual elevation difference between us, like in reality. So that's where the occlusions would work out. Now, when we consider refraction here, when we look at that and go to different peaks, it's never consistent with the amount that the central angle is off for either of us. It's strictly a relationship between the rise over run to the peak and rise minus globe drop over run to the peak. So, but anyway, refraction is obviously included in the analysis there for showing, how it'll be geometrically over the peak at the time of occlusion or already under, etc. Which doesn't lead to an occlusion, doesn't cause an occlusion, doesn't define the GP of a star. So it doesn't, we don't consider it, but it is in there in the analysis, but it's not congruent with the angle offsets. So,
So it's kind of just arbitrary.
yeah, because it's like the premise that when it's physically intersected, it's no longer visible for the observer seems to supersede any amount of what refraction would hypothetically do or not do. Because otherwise, the half gamma airs uh, would be offset between us by a more proportional ratio to the refraction amount.
Some
But it,
relationship between those, right?
yeah, and keep in mind, if there was no mountain peak there, they, that would be the quote unquote angle that it would have to be for that, or like the amount of refraction rather would have to be whatever it is to explain that angle, because that's how the whole system works essentially. If you see something in the sky, then where it's not supposed to be, it's a refraction error, and it's always the exact amount needed to explain it. So in this case, it would just be cutting off the amount of refraction to just say that it just looks like the Earth is flat, which is an interesting position. But yeah, that's where we're at. Oh, and I did add, before we'll get into Q&A and stuff, obviously, because that was kind of dense. But before we get into that, I did add sidereal calculator to the occlusions or whatever. Somebody had asked many cell theos ago if there was a relationship between the occlusion offsets and sidereal time, and there is. So I noted that here with sidereal calculator 1. I just added, this is just for testing right now, but the other ones will be added in case anyone is interested. But anyway, you can come here, select your peak, or what is that, your star relationship, and then it'll give you the occlusions for that peak that happens. So if two stars, I'm sorry, if the same star hits a peak on different days, you can take the difference and their occlusions, and you get the sidereal offset, which is 235 seconds, about 3 minutes and 55 seconds. And then there's another way you can do it that we found from how the French used to do it. We mentioned it here a couple of weeks ago, where we found that document from, what's his name, Chavante or whatever, Chavant. And he was saying that the French use this method of timing two occlusions and then taking the timing difference from that and ratioing it against solar time to get what the sidereal difference would be. So in this case, we took an example at Pikes Peak here, where two different stars hit at the same day. So we just have like the same day timing offset. Theoretically, you could do as many days apart as you want or whatever, because it's just going to get converted into seconds and hours and all that. But anyway, we have the timing offset here, and then so for 48 minutes of the hour, there's a 7.95 second offset to add to your solar time to get sidereal time. So that's pretty interesting. It's not um, it's not like let's see, just different
An
ways you
add-on.
can, just different way. Yeah, there's just kind of cool, just a neat tidbit or whatever. Because what happens is, if you change both of these proportionally, it would still give the same offsets or whatever for sidereal time. So it's not like a super rigorous verification of anything, but it is an interesting facet of the difference in the speed of the sky versus the speed of the sun.
I have a question, Alan.
Absolutely.
Like in just like simple time, right? Like, could you lay out like according to the what's the difference between just time, like how like 1 second between globe prediction and actual sighting,
Yeah.
or
Yeah. So they were a minute and 15 seconds off on their occlusion. It should have happened earlier.
that's a lot. Yeah, that's a lot of time. So a whole minute and 15 seconds off. Wow.
Yeah.
Okay, thank you.
Yeah.
And that comes from the 13
Yep. From
arc
this
minutes,
from this
38 arc
exactly.
seconds.
Now remember,
Yeah, I would say that's not even close. That's not like, listen, we were just a couple seconds off. That's a whole like a minute and a half. That's a long time to be off. That's a
and
ways off.
right. And remember, like, flat Earth is off too, but we're only off because of the like, it's a proportional ratio to that arc length. If it had any correspondence to the globe, the errors would
It'd be
be,
opposite.
it would be literally reversed. So
Okay,
the fact
that
that,
minute and 15 seconds, is that the discrepancy between the prediction and the globe, or the flat and the globe?
no,
Yeah,
this is
or
this, it's the discrepancy between what the globe predicts. And the leftover error, I'm saying, is like a mathematical artifact, because it's just It's how much is left of the
Arc length.
of that gamma of the arc length at the time of occlusion. So they're actually off by the full 115 because there's nothing else there, at the end of that peak, unless they want to say that the peak elevations are off, and which I don't think anyone wants to do that.
So just keeping that example there, I just want to make sure I understand this. So you got the arc length, which is, do you have that listed somewhere? I see the half gamma.
Yes, the
There's
arc
the
length
full.
is down here, noted
There
here.
it is.
Yeah.
All right, so 27 arc minutes.
Mm-hmm.
That's equivalent to, what did it say, 229.
Yeah, it would take 2 minutes and 29 seconds for the star to drop relative to the observer. Like if you were to go in Stellarium and rewind time of the occlusion, if you go back 2 minutes and 29 seconds, the star will be at 233 for the observer. I've actually done that here on the Obsidian.
Oh, really? Okay.
Yep. That's under why the globe predicts an earlier time. I'll put that in the chat. But yeah, if you go back and rewind it by 2 minutes and 30 or 2 minutes 29 seconds, you get that angle. And then so if you play that back out, to the time of occlusion, that's the end of the arc length. So it's either going to be lined up with what the globe predicts for its physical geometric intersection, or what flat Earth predicts.
Right.
Because there's only two things there. There's either a mountain that's rise minus run, or rise minus globe drop over run, or just rise over run.
Right. And the arc length is defined by the occlusion and the observer. You got the observer,
Yeah.
boom. You see the star go behind the mountain peak. Bam. Right there. There's your arc length.
Yep.
Got it. And then that arc length is defined because the occlusion time is what substantiates it in reality.
The arc length is defined because yes, you could use the arc length, like adding the arc length back, will tell you where the star would be at that location. So yes,
You see what I'm saying though? Like that's
it's defined between the observer and the peak at the
in
time
the
of
peak,
occlusion. Yes.
the time of the occlusion, right?
Yeah,
So
no,
that's how
I
you're,
see what you're saying. Yeah.
yeah, it's like that's locked in.
Yep.
I got you.
Yeah. And so if you were to do like a complementary angle off of this, there would be, I think what Eludis and I were talking about that last week, it would be like 89 something, or no, it'd be 87 point something or whatever. But in any case, that would complete the 360 geometry for the, for everything to be relative, for the star to be moving at 1 nautical mile per degree, like within the coordinate system to, where it should be. So yeah, it's defined by that arc length. It's a good way to put it. It takes a little snapshot out of the whole circle there.
Slice.
And it's relative to that exactly. And then the half gamma of that defines what the
Drop
drop
over distance.
would be for that peak. Yep.
Professor Phil, have you been following along somewhat? Any questions? I know you're probably doing something as well, but I just definitely want to hear the other side's take on it, if any. He's chewing on it. Okay, he's chewing on it. Cool.
Nice. Yeah, if you have any questions or whatever, feel free to send me a DM and I will get back to you. And there's a Obsidian page here, Introduction to Cell Theo, and it's got some other resources and links that you may want to, like if you have questions or whatever, you may find the answers in those. And here's a link to the old spreadsheet.
Sorry, I don't have any useful questions because I couldn't listen to all of it. I've got a lecture on at 3 o'clock, so I'm just hurriedly just trying to get that done.
No worries,
So
lad.
sorry, I will if you've got a video or something I can watch later, or a podcast I can listen to.
Yeah.
I'll gladly do that.
Yeah, for sure.
Okay, all right. So DM me if you don't mind with your video link for your podcast, and I'll gladly do that and give you my honest opinion about what's going on, and unbiased as much as possible.
Thanks, lad.
Okay.
Sounds good. Sounds good.
What would be a good one?
All right.
Yeah. All right. So send that to me, and I'll do a presentation, either agreeing with you or rebutting you. Okay?
Nice.
What's your PhD in, Professor?
In particle physics.
What did you say? Sorry, particle physics.
Yes. Okay, I've got to finish this lecture. I'll see you guys later. Thank you.
See you.
Okay.
Thank you.
All right. Bye-bye.
All right. So let's see. So yeah, I know that was kind of math dense to go over and stuff, and I will do a better job next week of having more of it broken down. I spent a lot of time like refiguring the whole situation out, because I was actually, like I said, I had a misconception going on where I was adding the two half gammas back together and thinking that was like equivalent to gamma, which numerically it is, but you don't add that's not that's not the proper use of that. So anyway, I had a lot to learn. So when we'll come back next week more prepared and break it down easier, because I think like the barrier for entry really comes down to central angle theorem, which is fairly straightforward, I would say. And I think if I do a better job articulating it, it'll make more sense to see what we see out of it. But if there are any questions or anything like that,
Yeah, Alan, what
So
field would
send me
this be
that.
in if you wanted to study about the topic? What field at university would you have to study?
just math, I guess. Like you would have to. It's all.
So not particle physics, right?
You'd have to study. You'd have to first study mathematics. By the time you get to study particle physics, which is a very, very broad field, you'll have covered a lot of ground in many areas, and that's why I teach in a lot of areas of physics, so it covers a lot of areas. Okay.
Yeah,
All right. So I'm really interested in what you in that presentation that you did. So I'd really be grateful if you would send me a link to that, so that I can more closely follow it. Okay, because as I said, I have been preparing for a lecture in 3 o'clock, so it's not very far away, and
yeah, you're good.
And I've got to get that ready. So so if you can send me that, I will. After this lecture, I'll have a look at it, and then I'll come back sometime, and I can explain to the rest of everybody who wants to listen what I think, and and if there's a rebuttal, there is. If there's an agreement, there is. Okay, so I'll be as fair as possible.
Every Monday, Professor Phil.
Sounds good.
Okay.
And
all right.
Let's see. And
okay, so I've got to go. I might just stay listening, but I can't interact anymore. Okay.
Yep. No worries,
Later,
lad.
Professor Phil.
Thank you, sir.
Okay, you're welcome.
All right. And good vibes to kind of add on to what he was saying. Like, yeah, by the time you get to particle physics, like you've already covered all the trig stuff necessary to handle this, because this is like the literal entry level trig stuff. So they would definitely have to have a slight grasp on it.
Yeah, what do you think I should send him? Oh, sorry, go ahead.
I just sent them the link to this, even though the opening was kind of dense.
don't forget orbital mechanics is in my wheelhouse too. Okay, so I can discuss it I can look at it from that point of view.
Oh, dude, yeah. I mean, you probably know a lot about central angle theorem then with ECI transfers and
Of
stuff. So
course,
there you go.
naturally.
So yeah,
Okay.
you have all the tools necessary to grasp this.
I do. I'll be as fair as I can and see what I think. Okay.
Nice, dude. Looking forward to it.
All right. You're welcome. Okay. Please send that.
All right, I did.
Mayor Skater, we got a PhD on the hook. Got him.
Oh, yeah. Then you guys want to see something cool? So there might be some up and coming new footage that'll look a little bit like this in the future. Very excited to get more star occlusions. That looks insane.
Wait, what is that?
Infrared.
Oh, is that from the guy you were talking to?
No, this is just some dude on YouTube, and I was like, because I was looking for infrared stuff for occlusions and whatnot, and this is the kind of quality we can get out of it. This looks so much better than the Z star. Like here's the horizon. Look, it's going into the tree. That's so sick.
What is
That's
that stuff flying around?
Yeah, dog. That's I assume SpaceX stuff, or not SpaceX. What's it called? Starlight, Star Bright, Star Night.
Balloon Link.
But yeah,
And some of them are probably aircraft too.
yeah.
There's some weird flight paths, though. That's for sure. Oh yeah, they do look like flight paths. Actually, yeah, you can tell.
Yeah, there's all kinds of stuff going on up there. It looks very cool.
Oh, the way it's turning, the way the sidereal motion's going.
Yeah, that looks awesome. So look forward to that. Let's see what else we got coming up. I think that's about it. And if there's no questions or anything to add on, like I said, we'll come back with more diagrams to kind of break down those basics and get your foot in the door. But yeah, it really comes down to they missed their intersection window, and they're always off by like the refracted amount. Like even if you go to the star emergence uh, where the quote unquote globe was measured and falsified the method and all that, the place where the true position and apparent position intersect at the peak or whatever. But even in this scenario here, we end up, so the globe predicts 11 arc minutes of drop over distance here for this. We end up being off by 12. The globe ends up being off by double. And subtracting the amount here comes out to be the drop over distance. So even on the emergence, where the refracted position would already be almost 3 arc minutes above the peak coming in for meaning it would have emerged 17 real seconds earlier. It didn't even do that until the arc length was fully traversed. And then again, that air difference ends up being on the globe. They got twice the air out of it because the star was literally blocked by a mountain. So
An awesome presentation. I really look forward to, credentialed folks looking it over with a fine tooth comb and giving constructive feedback, criticism, or like the gentleman said, the professor agreeing with what he can't agree with. This is exciting.
yeah.
What's up, JT?
Just listening in, enjoying.
So, oh yeah, there will be an upcoming debate too on the celestial theodolite with Astronomy Live.
Oh wow, that'll be sweet.
Yeah, that'll be fun. He's gonna do it after the Artemis 2 thing wraps up. So he said that's when his schedule will be available. So I think that'll be sometime next week. So maybe next week the debate we'll have a date or whatever. I'll keep you guys posted.
I look forward to a good debate, and then hopefully Bruce from Mindshot can break down who is logically consistent and least fallacious.
Oh, that'll be fun.
Good presentation, brother.
Yeah. All right. Shane, are you still there? He's like, oh shoot, nice calling on me.
He's running back to his mic right now.
He's not playing with his dog. All right. Well, I was gonna see if he's been on Facebook doing a lot of Q&A and stuff with Cell Theo. So I was gonna see if he had any good questions or whatever to just throw out answers to or whatever. But yeah, we'll go ahead and wrap up, I guess. Thank you everyone for coming out, and we will resume next week. So see you guys there. And then tomorrow night will be it'll be either a research and reading night, or if we're lucky, Goose's schedule will line up with ours and he can go over his measurements that he did using a ruler and a laser to I actually don't even remember the whole process, so I can't even articulate it. But basically, it's a homemade theodolite that somehow measures the flat earth angle prediction versus what the globe would predict with an actual theodolite. So we'll get into the specifics of how all that unfolds. But he apparently reproduced the measurements and has some stuff to go over. So that'll be either tomorrow night or next week. So see you guys.
Dude, dope.
We'll see you guys for that. Yeah, it's going to be awesome. And that's another thing that Heffron came up with.
Someone was about to respond. I heard someone.
Yeah, I've got a quick question.
Yes, sir.
Um, okay, in the animation that Shane posted, I'll post it in the chat once.
Mm-hmm.
So in this animation, it's supposed to be showing the prediction of where the star is occluded on a flat Earth and on a globe Earth. Why doesn't it change to a flat Earth for the flat Earth prediction? It's showing a prediction for where the star is occluded on a flat Earth, but from the globe.
Well, the relevant part of that animation is just the star elevation for the peak alignment. So we could technically change it or whatever, but it's more about the position of the elevation rather than the topography of, what it is. And it would kind of be confusing if we changed it.
Well, it just makes no sense, because if you're predicting where the star would be occluded on a flat Earth, why would the mountain peak be in the same position as it would be on a globe? It would be a lot higher on a flat
Yeah.
Earth.
Well, like I said, the elevation differences are in the numbers on the alignment versus the actual visual image. Like it's just kind of meant to be a visual
Yeah, it's just
aid.
a representation. Yeah.
But your
But
point's noted.
it's on a globe Earth, the mountain peak would be lower,
Correct.
and on a flat Earth, the peak would be higher, meaning that the occlusion time would be sooner on a flat Earth than it would be on a globe Earth.
Oh, no, it would be later because the star is already aligned with the peak at the for the observer because they're already tilted towards it.
That doesn't make any sense, because on a flat Earth, the peak would be higher, so the occlusion time would be before the globe Earth occlusion time.
Right, but the star is following the observer, right? And the observer is tilting away, as the Earth rotates out from underneath the star. So that geometric alignment for the observer to the peak is going to be sooner than what flat Earth predicts. And I could show
How would it
you
be sooner? How would it be sooner if the flat Earth peak would be higher than the globe Earth peak?
Because you're rotating beneath, like in your paradigm, the Earth is rotating.
because on the globe half of the work is already done. I'll send
Yeah.
you this link here to my Obsidian where I went over this. Just hang on a second. I know. But if you read through this, I have all the timestamps. You can go through in Stellarium and like, confirm it for yourself too. But everything that you're about to ask is all on this page. And you could
How could you
see for the observer when it aligns with 217 versus when it
how
aligns with the peak at 230.
but how could Stellarium ever display any prediction about the flat Earth when it's a globe in Stellarium? How can you use
Okay.
Stellarium to know where the peak would be on a flat Earth if
Are you
it
gonna
doesn't
click
make
on
any
that
sense?
link that he posted?
We don't do that, right? The rise over run to the peak is independent of whatever we're doing in Stellarium. The Stellarium we use to confirm what the angle was at when the occlusion happened. We don't we don't account for anything like that in Stellarium, like what you're trying to or what you may think we're doing. It just so happens that when you add the arc length back, right? We don't even have to go into Stellarium and change positions or anything. You could just add the arc length back, and if it equals the rise over run to the peak, then that's it. It should never equal that on a flat earth. And it's like, and I gave earlier during the presentation, I went over what it looks like for the globe. If you're able to see my screen right now, right, because the occlusion happened later than what the globe predicted for the geometric alignment, you see this offset, and you see that flat earth is closer for the geometric alignment when we add the arc length back to the star's position. And then if the earth were a globe, we can show you what that would look like here. Now look at this air difference here. You're going to see this 13, or you're going to see this 11 and this 2 become a 13 for flat earth because the occlusion would have occurred earlier when the star was geometrically aligned to the peak. So here we go to that. And now the air gets reversed. The only way the air would get reversed is if there's no drop over distance, because the elevation uh, isn't going to line up for the star at that angle, because it's just apparent. So the actual intersection with the source happened with the rise over run to the peak at the end of that arc length. That's the only reason. That's the only way that these could be reversed in difference over the same arc length. So
Okay, but okay, if we take and we look at this, there's going to be a certain peak. There's going to be a certain height that the peak will be on a flat Earth, and then there'll be a certain height that the peak will be on a globe Earth. The peak on the flat Earth will be above where the peak would be on a globe Earth. Yet you're saying that the occlusion would happen on the globe Earth before the flat Earth. It just
yeah,
doesn't make sense.
yeah, because the observer is already offset by the curvature to the horizon. So
What does
it's
that have to
so
do with anything?
because as the star is descending, it's going to intersect with that lower angle at the time it does before it would for a flat Earth.
How could that be if the peak's below where the peak would be on a
Hey,
flat Earth
Because
on a
check it
globe?
because
out.
because on a globe, the star is supposed to be following the observer centric position. So if the star is truly following 60 nautical miles per degree at 15 degrees per hour, plus or minus latitude variation for the 60 nautical mile part. But if that's all true and is following that geometry, because the Earth is a ball relative to the observer, that intersection angle occurs before the peak or before the star is able to align with the peak. So if you look back at the difference here on a globe, what would happen is the geometric alignment would occur with respect to that half gamma amount, which is the drop over distance of the arc length between the observer and the peak. So when you add the full arc length back, the flat earth prediction would end up being off by that curvature amount, that half gamma, and it puts it up at 244. So I know it might sound like not what you would expect, like intuitively, but you got to remember the star for the observer, based on the geometry of the globe, that star is already getting low. It's already, it has to follow a certain rate, so relative to that observer, so it's going to align with the peak earlier. And if the
Yeah, that still just makes no sense because geometrically the peak would be higher and above on a flat Earth than it would be on the globe Earth. So it still doesn't
okay,
make any sense
okay, imagine,
why would
okay,
include.
okay, okay,
Can I finish what
try,
I'm saying?
try
It just
not.
doesn't make any sense.
I
Okay,
got you.
whatever. Just don't talk to you. I'm done. I made my point. So
I'm not trying to overtalk you. Just try and think about them separately for a second instead of together. So just think about what the globe would predict separately. So the globe, there's no big occluding thing above it or whatever, right? There's just what the globe predicts. Okay, so the mountain is already at a lower elevation. The star is descending into that lower elevation relative to the observer. Okay, when those two geometric alignments occur, that alignment is a minute and 15 seconds before what the occlusion was. So it was aligned geometrically from observer to peak to star at that earlier time, and you can get at this 1842.04, and you can go through, and as you read through that link I gave you, you'll see what the observer predicts, on a globe for that timeline. And that's basically it. And then so for the flat earth prediction, right, we can't follow that geometry to get an occlusion. We can't follow 60 nautical miles per degree relative to the observer to get an occlusion at the same time that the globe predicts, because we're supposed to be higher, right? So for us, the star has to travel longer to be
Occluded.
one second. Sorry, the elevation is, it's not that it's like traveling a different distance, because the arc length is still the arc length. This is like the problem I was having earlier, why I got mixed up. So the elevation difference, right, relative to the observer, if it's following that 60 nautical miles per degree, then it's going to occlude earlier. If it's not following that, then the occlusion happens later at a when it's at a different alignment relative to that arc length, and that happens to come out with what the closer to what the flat earth is for the rise over run. So the only way that mismatch would happen is if there was no globe occlusion at that earlier time predicted when they had their geometric alignment. Because any time after this, there's no geometric alignment for the globe. There's one chance where they could have that congruent triangle to substantiate. Anytime after that, it doesn't work.
Yep.
So it might not sound like what you it might not sound like what you expect, but basically on flat earth the stars aren't following the 60 nautical mile per degree descent, and that lingering, because they're just for us, they're just moving away from us, and so they're not going to follow that relationship to go beneath you, and that difference is what's being measured here. That's why
so
it's
why
yellow.
do
It
we
takes
observe?
longer.
So why in reality do we observe the stars moving at 15 degrees per hour?
Well, you could either say Earth rotation or sky rotation. I think the better question that you might be trying to ask is, like, why do the stars set, maybe, or something?
No, you just claimed that because the flat Earth, the stars are just going away from you and not following that 15 degrees per
Oh,
hour.
I see. I got you.
So why do we observe them moving 15 degrees per hour, but yet you're saying, oh, it's like
Yeah.
you're confusing up the whole thing just to say that, well, it's not really what we observe in reality. So it can follow these other types of physics or whatever it is you're trying to explain away why it just
Gotcha.
doesn't make any sense.
So on a globe, the stars have to be, coming with parallel light rays, and then the geometry of the Earth changes how you perceive them, right? On a flat Earth, the sky is just perceived in curves as a feature of our eyes. You know, we would say that we just see in curved visual space, and that creates the effect of the stars that we see, even the latitude dependency of them. So beyond that, I don't have an answer for you as to like why we perceive them do that, but the globe asserts that it's due to parallel light rays and the geometry of the Earth, whereas we say it's just, you know, how we perceive them. And the difference in our predictions is the half gamma. So it's really interesting that the error in every measurement is that the is predicated on the globe being off by what they would have predicted as curvature.
So be damned.
Oh, 1 second. I have to turn you up, Jake. Sorry, go ahead.
You acknowledge that on an equatorial mount, you can zoom into a particular star or planet on any location on the Earth, and with one axis of rotation, you will be able to track that object from when it rises over the horizon to when it sets.
Well, you have to
On
align it
one
you have
axis of rotation.
you
Once
have
you
to
once you
you
once
have
you
to
align
align it
it,
to true north, so it's still two
once you align it
axis.
to north, which would be strange on a flat Earth, that when you change in latitude, you have to change the axis of rotation of the sky. On a flat Earth, that doesn't seem to make sense, because if you put a bowl over a flat sheet, and you like have stuff moving on the bowl, it would be the same for all observers on the flat Earth. How would the bowl be tilting differently for different observers on the flat Earth?
Well, it would be relative to the source of the projection, I think. So that's my answer for it.
I mean,
It's
even if you
latitude
set up
dependent,
a little,
and based on
even if
where you're at is how you're going to perceive the sky.
even
So
if you set up a little projector, a miniature
So
projector
one
into,
second, hang on. Before we move on, though, one of your key points was that it's single axis, and then we just went over how it's two axis, so it's not mutually exclusive in that regard, which was a, you have to align it to the North Pole, so it's still two axis. You don't get a free axis by having it already aligned to another point. Yes, you're aligning it to 2 points, one to the north and one to the star.
You're aligning the axis to the pole, but you're still the mount only articulates in one axis. It only has 1 degree of freedom.
Yeah, after you've aligned it to another axis, though. So, like, I'm not gonna
he's ignoring that.
like if you just ignore that, then that's like I don't know what to, that's cool, man.
It literally
So,
says two on
so,
an equatorial mount.
so again, the mutual exclusivity of that is gone. And as to answering the question as to the latitude dependency of the stars, I'm not sure, but I have working hypotheses on it. But the point of it is, regardless of how we see the stars, like causal mechanism wise, on a globe, these occlusion timings would behave differently because the geometry of the ground is assisting in the sky. So, we've shown what the measurements would look like if the intersection occurred for a globe, and how that would change the air position. So I don't really, when you say it should look XYZ, it, maybe, but also if the Earth's a globe, this should be reversed mandatory every time for all the measurements. There's not even ambiguity in them. Every single one of them is the globe is off by what they predict as curvature. So
Yeah, I don't know. Hey, Jake, do you want to explain to Ecoplex, if you can, why the globe would have an earlier occlusion time?
What do you mean?
Do you understand why the globe would have an earlier occlusion time?
Occlusion time compared to what?
Oh, look, Shane did it. There you go.
nice, Shane.
What are the two
Nice.
scenarios? Set them up
Flat
for
and
me.
Observer-centric,
globe.
observer-centric geometric intersection from true position to star to what globe predicts as the elevation of the peak. versus rise over run to the peak where the star is where the arc length is added back to the star's true position from observer location. So basically, one of those should be off by the Earth curvature amount, essentially.
Dude, Mac and Cheese actually had a good steel man right there.
What was it?
He said, I believe he's claiming that the time necessary for occlusion on the globe, with the mountain being lower, caused by the Earth's rotation, is shorter than the time necessary for occlusion on the flat Earth, where the mountain isn't physically lowered from the tangent plane and is caused by the star's motion away from the observer.
Oh, dude, where's that guy at?
Yeah, but there's no disagreement from anybody that once you're far enough away from that mountain is considerably lower in the horizon from the observer compared to the rise over run formula would predict. Like if you're looking at Mount St. Helens from from wherever, Oregon or whatever, from 300 miles away, where you can still see, or I forget from what distance you're still able to see Mount St. Helens, whatever that is, 150 miles. That when you measure that, if you use a theodolite to measure the top of that mountain from that distant observation, that altitude angle is going to be a lot lower than what rise over run would predict.
No shit.
Why would that be, Jake? Why?
Because the Earth is a sphere and the mountain is dropping with the curvature of the Earth.
How do you know it's not an optical effect?
How do you know it's not an optical effect?
Because you can predict how much that, if it is a purely an optical effect, knowing the properties of the air and refraction, we could come and look at wildly different atmospheric conditions between, the summertime, the wintertime, etc. Drastically different density altitudes, and see how much that changes. Because if this is all caused by that, by this atmospheric refraction, then we would see a much bigger change than what we actually observe, if that can account for the huge discrepancy between the flat Earth prediction and the globe Earth prediction.
Yeah, but there's one height of the mountain, correct?
Ooh.
There's one objective height.
Ooh, and
Sure,
real quick,
yeah, there's only one objective height.
Okay.
And real quick, we took measurements last year in July, and then we have the how much celestial or astronomical refraction they say there should be, and then we took measurements 6 months later in December 31st, and different temperatures, different times a year, and the refraction difference between the change in degrees was only, I think, 40 arc minutes off the top of my head. Or I'm sorry, that would be an insane amount. 40 arc seconds.
Yeah, 40 arc seconds.
Yeah, it's like 40 arc minutes. Yeah, anyway, it was only 40 arc seconds. So, yeah, it didn't. And on top of that, it doesn't change. The ratio to how much gamma is off isn't substantiated by the refraction amount.
Ever.
So,
Actually, so you're saying that refraction isn't that big.
Actually,
you're saying in this case, it doesn't look like, even under drastically different density altitudes, with knowing the properties of the coefficient of refraction based on the density of the medium, that we should expect, if this is what's accounting for why there's such a discrepancy between, the flat Earth rise over run prediction for the altitude of, for the elevation angle of Mount St. Helens from 200 miles away or whatever, to the globe Earth prediction, and accounting for why it's so much lower observably, right? Then we should expect that the refraction would be drastically different between different coefficients of refraction, if that's really what's accounting for that huge change, right?
I have no idea what you said. All we care about is the geometric alignments. So what we would look at in the Mount St. Helen thing is just the rise over run to the peak and the rise minus globe drop over run to the peak, and see where the true positions are closer. If it's closer to what the globe predicts from the observer, or when we add the arc length back, is it closer to what the rise over run predicts? Because the refraction amount doesn't have any correlation to the discrepancy in half gamma. So it appears to be largely irrelevant, meaning whenever the star actually intersects with the peak, at the end of that arc length, it's over. There's no more star.
Really?
And
Even when you don't see it?
if it was proportional to if it was proportional to the amount of reported refraction at the time, then the gamma offsets would be, would show that proportionality, but they don't. So.
You do understand, right, Jake, that you can argue
like
refraction all day and night, but the reason why the mountain peak is important is because it's using a physical geometric intersection to determine which prediction is correct. You understand that, right?
Yeah, but you can't take away, even if the mountain is occluding the star, right? That doesn't mean that you're not there's no refraction that's going on with regards to what that
Did
occlusion
anyone
angle
say
is
that?
between the observer.
Did anyone say there's no refraction? Did you hear me or Alan say that?
No, he says that every week, though. It's the only thing. Everything he
It's
says is
fucking
framed through
annoying.
that. Yeah, it's retarded, but whatever.
It's not.
Okay, I
It's
don't have
not
to participate in the
significant
conversation
enough.
then. If I'm just
It's
going to
not.
be insulted, you guys know I have a low IQ, and then you guys rub it in, and it drives me nuts.
Okay. How would you figure out how much refraction is between the mountain peak and the star?
I don't
From that
know. I have a
observation.
low IQ, so I'm not able to make that determination.
Oh, don't be butthurt. Come on, dude.
That's true. I've told you guys that how
Yeah.
long?
No, it's true. You did use a lot of big words. I don't want to call you on it, but you probably didn't know what they meant.
No, I don't know what they mean.
Yeah, but see, this is just a cop out. That's not cool.
It's not a cop out. How many times have I told you guys I struggle with this stuff?
All right, we get it. You struggle with this stuff. Refraction. You wanna say that it's a major player. So how much it should be between the mountain peak and the star?
I don't know. That'd be a question for a surveyor that has training in it.
A surveyor. We're talking about celestial refraction, bro, not terrestrial. Astronomical refraction.
Sure, but a surveyor could apply a correction for that, right?
A
Not
geodetic
talking about.
surveyor, perhaps, but not a plane surveyor. They're forbidden by the ancient text of I'm just kidding, but there are like rules against it or whatever. But yeah. So, there's a couple of formulas that they give for how much refraction there should be at a given angle when you're, looking at a star. And so what we found is like these formulas, like the backbone of them is basically but it's model fitting and curve fitting the how much refraction there needs to be to explain why this observation is still visible above the horizon when geometrically it should be below the ball. Like there's an example here of North Peak where the star's true position relative to the observer is negative 12 arc minutes. And if you're familiar with the celestial and terrestrial sphere, you'll know that when something is negative coordinates, it's below the celestial horizon, so it's like geometrically under the half of the ball at that point. Like like if you were standing at the North Pole, this would be 11 or 12 arc minutes under the equator, under that midpoint of the equator relative to you. So they're willing to say that if you happen to see the star at what was it 12 arc minutes above the horizon, well, that's because it's being refracted 24 arc minutes. So they've dedicated 12 arc minutes of refraction to lift over the ball from the equator to get over the celestial horizon, and then to get you up into your horizon where you see it above the horizon, they add another 12. Right, all that comes out of all that comes out of formula that basically has input and boundary conditions of the globe. So everything that comes out of it it's going to explain this angle difference as this much refraction because that's how much has to be there for it to make sense on the globe. And so these numbers don't come from any sort of like actual measurement. Now you can put your temperature and pressure into these equations and it will adjust the variable by a couple of like depending on where you're at, it'll be like an arc minute or arc seconds. But basically, this is how much there has to be, and it's never that amount to lift it over the peak. Like it shares no relationship to the difference at the time of occlusion. And so that's you end up in scenarios where they predict that the apparent position is actually still above the peak, so it would take longer for it to set into it, and that that's not what's observed. There's an immediate occlusion after that arc length is gone. So don't feel bad or retarded or beat yourself up about it. It's all good.
Took line. I mean line. Sorry,
It,
took
it took
Alan
it took me
year.
a year to get this far with it and understand it, and it's actually coming back every week and talking to the boys and getting feedback and having people give pushback and stuff has actually pushed me to understand it better. So don't feel bad if none of this like makes immediate sense to you. It takes time to get it. So
Yeah, Jake, you should
Thank you for
understand.
coming every week.
Sorry, go ahead, Rob.
No, I was just saying thank you for coming every week because I learn more and more about it every time. I still hate looking at lights in the sky as a proof for flat Earth, but I am starting to understand how this works every week.
nice.
Thank you.
Yeah, it's one of my favorite ones because at a certain point you'll come to the realization that you can't tell how straight a ruler is by just using the ruler itself. You have to have another reference, and when you get to that point, the Earth, one of the only, I think the only external reference we have really is the stars. So, and that's what they've built their entire model on, So.
Yep.
Or water. I use water.
Well, right,
like
but
water.
Right, but how flat's flat, Like how flat is the water? Because they would just, redefine it by a slight curve over distance that's imperceptible. Like,
I know.
like,
I
yeah,
understand, but I use water as the reference for flat.
gotcha.
But that's just me. That's just me, and
It's not.
I'm
It's not
allowed
a
to
bad.
do that.
It's not a bad one. It's hard to argue against.
I know. Unless you think that when you say Earth, you just
This is
see a
just another
ball.
bullet gun.
Yeah, it's just the thing is that's so damning about it is the stars being an absolute reference for anyone anyone on Earth. Literally, anyone can look up in the sky and see the stars. We all see it objectively. We all see the same relationship of the sidereal time versus local noon time, or just we have a clock in the sky, and that timing.
Absolute,
What'd you say?
accurate clock.
Yeah, an accurate clock, exactly. And that timing is hard to argue with. So, I mean, there's only one specific time where a star is going to appear to the observer at a certain location to quote unquote set. You know what I mean? Behind a mountain peak. Because like, if there was no mountain peak there, Jake, right? If there was no mountain peak there, you would say that the lingering is because of refraction. That star hasn't set behind the horizon yet because of refraction. Refraction's lifting it back up over the ball curve. Right? Yeah, I agree with you. Yeah, totally. Yeah.
Totes.
Toast my goats.
All right, lads, we're gonna go ahead and wrap up here. Thanks for everyone coming out. We'll see you guys next week, and then tomorrow night will be reading night and/or Goose's thing on the man-made theodolite.